Well, good morning, everyone, and welcome to this webinar. Uh, this is, I think, quite an interesting topic we have today. So we're going to talk about, as it says, understanding powders, soils, and bulk material behaviors with Altair EDEM. And as you can see here in the title slide, many different examples of working with different types of bulk material and different particles of different sizes. So what is Altair EDEM? So the DEM stands for discrete element modeling, which speaks to the different particles that are being considered. And the reason this type of simulation is really so interesting and being more and more used is that we now have the computer capability to be able to look at many particles. And I think, to look at thousands of particles is useful for certain things, but we now have the capability to look at actually millions of particles. And actually, Altair recently did a study where they used some high performance computer hardware and actually did an EDEM simulation with 1 billion particles, which is a little bit mind boggling. But I think in many cases to look at maybe 1 million particles or a few million particles can really yield a lot of insight into the behavior of these different types of systems. So today we're going to look at some applications of these DEM simulations, and then we are going to look at a detailed case study of using EDEM and DEM techniques in assessing the behavior of a U.S. Army off-highway vehicle, which is just one of many possible application areas. And then we'll have a little bit of time for a Q&A. So let's look at the different challenges that occur in bulk material handling. As we have bulk material, it's maybe some kind of a process, then we can have issues of the particles clumping together in some fashion. So terms such as rat holing, arching, bridging, all describe how these particles can bunch up and not flow smoothly. Second challenge is that of segregation, where in cases where we have different size particles that are interacting with each other, then they may segregate into different portions of the volume, and then that will influence the behavior because it's no longer a homogeneous collection of particles. Another interesting challenge to address and to gain information using DEM is that of equipment wear. So as we have mining and construction equipment that's pushing around dirt and soils or maybe some kind of ore, then there's certain loads that are applied to the mechanisms and the machinery. And using DEM techniques, we can get a true idea of what are the loads on the equipment, and we get much more insight than we would by just assuming like a single point mass type of load. Another one would be in trying to compact powders. Different things will influence that, and these things can be studied using DEM techniques. So what is discrete element modeling or using discrete element method? So we have many, many particles and they're all in contact with each other. And that's one of the reasons why computationally it's a challenge to do this, because each particle can potentially interact with all the other particles. So as the number of particles grows, then that's more and more collisions to check for and so forth. But special techniques are used to make that a reasonable thing to do. And in that collision, we have certain concepts of friction going on, also some kind of cohesion between the particles, and the setting of those parameters is what then helps these simulations be so accurate and provide such great insights. So what kind of DEM particles are used? Well, we may have bulk material in silos, so agricultural type applications, different cereals, grains. Uh, and so in the case of that, these agricultural particles are often, very much not spherical particles. Uh, we have things like sand, and those are closer to being spherical particles, depending on the region where the sand is. We have powders, and those can be quite fine powders. And I think good application for looking at powders often has to do with evaluating the mixing of different powder streams that are being combined. And then finally, we have these blocky or jointed rock masses. So they might be quite irregular in shape. And so with all these different types of particles, we have really the need to look at non-spherical geometry interacting with, maybe millions of other uh, particles with the same type of irregularities. So the particle shape, it's the basics here of EDEM is it starts out with a single sphere. And so, that can be computed very quickly, but it only applies really to quite narrow application areas. And then we have the multi-sphere approach, and that's where we take multiple spheres and put them together in order to form an irregular particle. But because it's a collection of spheres, then computationally it's still quite fast and quite accurate as well. And actually, in the case study, we'll look at the use of a multi-sphere particle to basically simulate the pieces of gravel that we're looking in our vehicle assessment. And then finally, we have polyhedral approaches, different polyhedron type shapes. And that allows us to simulate quite irregular particle shapes. And then with the different sides, then all those are available to assess different contacts and so forth. And not being shown on this slide is actually there's also the capability in EDEM to add some flexibility to these shapes, and that is quite useful in some of the agricultural applications, but it could be applied to a variety of other industries as well, where they may have some kind of a crop that flexes. And as we see on this slide, as we go from the left to the right, then we're increasing in sophistication and accuracy, but we're also ending up with slower computing times. And that's why it's so important to have the right computer hardware to be able to simulate these systems. And with the advent of the GPU processing, that enables us to get a lot of computing power really on a single card. So there's really a lot of great capability with this technology. So as we saw in the previous slide, we really can define any types of particles that we want. And we can have what are referred to as factories that are producing these particles into our environment. And so with the multiple factories, you can actually combine particles of different sizes and shapes all together. And so that might be basically a sort of pre-processing activity to first introduce all the different types of particles and get them set up to then initiate the simulation. It's also possible to have the factories adding particles into the simulation as the simulation proceeds. So with EDEM, we have what's known as the GEM database. That stands for Generic EDEM Material Model. And there's over 65,000 different types of materials. And these material models, with the characteristics and the shapes and whatever, have been validated. And there's different types of materials, the dry materials, sticky materials, compressible materials. And so in this database, then that's a good starting point to come up with the right types of parameters and shapes and so forth to represent different types of materials. There's an open architecture for doing scripting, including with Python. And the scripting is not only for model generation, but also for post-processing. You can co-simulate with finite element tools or multi-body dynamics tools or computational fluid dynamic tools. And our case study will show the co-simulation with the multi-body dynamics tool. And then as we saw earlier, we can do the multi-sphere particle shapes and the spheral cylinder types of particles. And then it's even possible to have these particles break up. And this Tavares approach is applied. It's the fastest method, and it's able to maintain the mass within the system as the particles are breaking up. The solutions run on both CPU and GPU, and on the GPU using the CUDA language. So, in the past, running on compute clusters with many CPUs was the best way to get faster simulations. But as the GPU technology has progressed with many compute cores on a card, and also the speed of the processing of the GPUs, for many applications, the the GPU approach is the most cost efficient way to go as far as hardware is concerned. But for those who have access to a CPU cluster, it's still quite possible to take advantage of that. So let's look at some applications here. We have construction mining equipment. And again, the focus there is looking at the behavior of the bulk material, either as it's moving through an operation or as it's being manipulated by machinery. We have agricultural machinery applications, looking at the behavior of the crop that's being harvested. So it could be grains, it could be like strands of straw or hay, different things being manipulated with the machinery and understanding the behaviors. Off-road vehicles, the application here is focused on the soil characterization, and soil modeling is extremely important to understand what are the mobility capabilities of these vehicles. And these kind of assessments are not easy to do in the field. So to be able to do that with an EDEM simulation is really a powerful contribution. Mining and material processing, again, a little bit similar to the construction and mining equipment, but once the particles, the ore is dumped from the machinery, then it goes through a process, possibly on conveyors or through passages, and to understand that behavior is quite important. Steelmaking also involves introduction of particles and then their behaviors. And then this last category is really a fast-growing category as far as people's usage of the technology, but it's in pharmaceuticals, foods and chemicals, and people are looking at quality of mixing, and this is really critical to product quality. And with simulation, we can come to a better understanding of what are the issues surrounding the mixing. Do we want to, change the shape of the different louvers and panels that the powders are interacting with in order to enhance the mixing? I mean, that can be a study. And then, the other question is, how long does it take for these different types of particles to be properly mixed together? And if one can optimize that and find out exactly how much time is needed, then possibly the process can be sped up, and then that can lead to higher value to the client at that point. So we've talked a little bit about the material library. One of the things shown here that's quite interesting is, looking at this angle that a pile of the material particles will make with the ground. And this is an important thing to check the accuracy of the material. So for example, if you have, round particles, just represented by a sphere only, then that would be like having a pile of marbles. And so when you release them, then everything will continue to collapse, and you'll have a pretty much a flat layer of marbles on the ground. So most materials don't behave like that. And why? Because they're not spheres, they're not perfect spheres. And also with the friction that causes them to be able to uh, you know, contact each other and hold their shape. So an accuracy check then is to pile up the material physically, see what this angle is, and then compare the results when you do your simulation. I mean, basically do a simulation just to replicate that behavior and check and make sure that's matching. So that kind of work has been done already in this GEM database for a variety, many different types of particles. And so there are specific particles set up for soils and also for powders. And so it's not just the shape of the particles, but also parameters involving the friction and the cohesion between the particles. All of those things, can and should be adjusted in order to have, accurate material that will, truly predict the behavior of the system. So, what are these different types of materials? I mean, we can have the really coarse material, and we see that with like gravel. We have the finer sands, and then we may have a material that's maybe composed of finer sands and maybe has some of the gravel in it. But imagine a clay type of soil where things are sticking together. So that's why you can see on the right, you can see all this material clumping together and so forth. Whereas the fine material falls off, and the top surface is quite smooth with the fine loose material, but with the sticky material, then things clump up. And it's can be really important to be able to evaluate that behavior. So what are the benefits of using EDEM? As with many types of simulation, engineering simulation, we really want to be able to understand what is going on with the system. And for many different products and processes, it can be quite difficult to see what is going on. Something is in our way to see things, and we may want to measure things, measure forces, um, different types of pressures, measure velocities. But in many of these systems, like the one shown, it's like, how do you instrument things to check for any of these pressures or whatever? Because you have the material flowing through the channel, and so then it would basically destroy instrumentation. So that's why it's so valuable to have the virtual testing and to be able to look at what is happening and basically be able to do cutaways and so forth. And we can colorize the particles for different types of characteristics. In this case, this animation, the colorization has to do with the compressive forces. So where the particles are turning green, that's where the highest compression is happening. And you can see how that's distributed over a certain range there. The other thing that people often do is colorize the particles for velocity. They want to know, where is the velocity high, but also where is the velocity low? Are particles kind of being stuck in certain regions? Sometimes that's like very undesirable to have that, and so you want to prevent it. Um, Other things are to look at any possibilities of blockages, and then also if the materials are going to a undesirable type location, you want to be able to identify that in advance, and also to understand the different forces such that one can assess how much wear is occurring to the machinery that's interacting with the particles. And then just to understand, how are the particles and the machinery interacting? Is it interacting in the way that we want? If not, then we can look at different design changes, change the geometry, change some of the forces in the machinery in order to produce the desired behaviors. And the great thing about all this is to reduce physical prototyping and testing costs. And one thing to keep in mind with this type of simulation is that to try to do physical testing as you do repeated tests, one will find that there's always going to be variation in the tests just because different environmental circumstances, even things like humidity, may affect behaviors, temperature could affect behaviors. And so if one is trying to do an engineering study and trying to figure out, what are good design changes, it can be very important to be able to identify, which of the possible design changes will have the biggest effect on the system behavior. So by doing things with simulation, then since everything is held consistent, from run to run, I mean, if you do repeated runs, you should get the same result every time if you're not changing any of the inputs. Because in our simulation we can hold everything constant. And then when you change certain input parameter, you can see what the effect is of that parameter all by itself. Whereas with physical testing, because of the inherent variation, it can be hard to determine what the effects are of the different changes. But here it can be quite clear. Now here's a slide that describes the integration we talked about earlier. So in looking at the particles, we may want to combine with other CAE technologies. So if we have flexible bodies involved, we might want to include those flexible bodies so that we can see what are the stresses in the system as a function of the interaction with the bulk material. We may have particles that are interacting with fluids. So we may want to introduce the computational fluid dynamics and have the integration. And then for the multi-body dynamics, that's where we look at the machinery, the linkage behavior, and to be able to study what the response of the particles are given machinery that has its own motion involved with it. So here listed are all the different tools where there's integration. So for the finite element analysis, I mean, you can see in bold here are all the other Altair modules that are supported by the integration. And then there's also some external packages as well. So for FEA, we have ANSYS and Abacus. For CFD, in addition to the AccuSolve, we have Fluent and OpenFoam. And then for multi-body dynamics, in addition to MotionSolve, we also have Atoms, Recordine, and LMS Virtual Lab Motion, which is now part of the Siemens suite. So today's case study is actually looking at Recordine interacting with EDEM. But you can see there's many options for all these different CAE simulation technologies. So what we're going to do here is the title of the case study is Addressing the Soft Soil Towing Capability of a Notional Recovery Vehicle Using Next Generation Modeling and Simulation Tools. So, here we see our notional recovery vehicle. It just has kind of a block body, showing that it's not really any particular vehicle. And what we want to do with this simulation is we have this recovery vehicle going up a slope that has a certain steepness of it. And what we're going to do is we're going to apply some loads to pull back on the recovery vehicle to represent what it is towing. And then at some point, as we increase the resisting loads, at some point the vehicle will not be able to continue to proceed, and that tells us what the capability is of the vehicle as far as what it can tow up that slope. So why is this being looked at? Well, so the Army is always concerned about having readiness, and so they want to make sure that their vehicles are ready to operate when needed, but also, in the case of the recovery vehicle, that there's a process to, recover any failed vehicles and to be able to return them back to operating status. So, having this availability means that the recovery vehicles are needed, but the recovery vehicles themselves must also be highly reliable. So in this case, we're going to use modeling and simulation to evaluate design changes that would improve this towing capability up a slope, and to use the insights from that to basically establish what could be done to actually have an improved vehicle in the future. So, background to the study, this modeling of soil has always been a challenge for off-highway vehicles of all sorts. And people have done different work looking at empirical models. And these are all references that are at the end of the presentation. Empirical models, semi-empirical models, and then kind of physics-based soil models like what we're talking about with EDEM. So really, the current state of the art is to apply discrete element method technology to study the behavior of the vehicles and their interactions with the soil. And that can apply to both wheeled vehicles and tracked vehicles. And, for each industry, the fact that these modeling and simulation tools are used in many other industries, that's very helpful because now there's a number of communities, a wide audience of people who are basically supporting the development of these tools, and we see continued enhancements of the software and their ability to run on fast computer hardware. So for this study, there's basically 4 steps, and those 4 steps are taken into account with these 8 different blocks here in the diagram. So, the first step here is to establish, what's a reasonable pintle force that might act on the recovery vehicle. And the pintle force is really referring to that resistive force pulling back, on the rear of the vehicle. And so blocks 1 and 2 are associated with that goal. So, to look at physical testing and to see what the different pintle forces are in actual tests is an important thing to look at. And then to analyze that data to basically determine what are reasonable forces to apply to the recovery vehicle. Second is to develop a soft soil subroutine using DEM simulations. So, in some cases, we can do a integrated co-simulation type of simulation where we have the DEM software running hand in hand with the other technology. In this case, since the soil behavior is fairly constant as far as, in different locations in space, then what we wanted to do was to characterize the soil as a function of normal force pushing down on the track, and also the side to side or front to back forces that are trying to break the track free from the soil. So the blocks 3 and 4 are looking at that, and so we had 2 different track pad geometries to look at. And then what we did is we used EDEM, and we used the material database, as we've talked about. And in this case, I picked out a gravel model that represented size of gravel involved. So as we look at the recovery vehicle going up the slope, it turns out that the gravel, the interaction with the gravel is the main driver for the behavior of the towing operation. And given the slope of the terrain, the finer grains of the soil, get washed off. And so then it's the top layer of the soil is primarily gravel. So what we did is we came up with a virtual test bin, and we loaded it up with particles, and we'll show animations of this in a few slides. And we applied a normal force to push down, and we had basically 3 track links or track shoes together. And so we pushed down on the 3 track shoes, and then we changed, the distribution of the front to back forces, and basically keeping constant the notion that there's a track tension on these tracked vehicles. So then we just changed the distribution of these tensile forces, from the rear to the front, and then continued to do that until the track links broke free of the soil. And by using a series of studies with different normal forces, and then doing the changing of the tensile forces, we were able to come up with some curves. And then we use those curves basically as part of a lookup table for what's called a soil subroutine in the multi-body dynamics software, which was Recordine. We use that to characterize things, and that was very computationally efficient, as we'll see. And then the third step is to validate the simulation data by using test data, and we'll talk about that in more detail. And then finally run separate studies where, now that we have the validated model, we'll now change some vehicle characteristics and then assess what the changes of those vehicle characteristics are on the towing capability. Okay. So in the pintle force calculation, here on the lower left, we see some sample test data of the pintle force. And as seen on the lower right, we're going to apply that pintle force on the rear. And actually, in this concept we're looking at, there's actually 2 attachment points. And so we distribute the load on those 2 points in the back of the vehicle. Okay. Okay, and then to do the soil modeling as I described, again, we have these 3 track shoes. We apply the normal force. And, the reason for having the 3 track shoes is that the front and the back track shoe are providing the right boundary conditions for the middle track shoe. And then what we're doing is we're measuring what's happening with the middle track shoe. So the front and the back track shoe are just there for setting up the right boundary conditions, but we're not using that particular data, just from the middle shoe. And so in this model, we had 87,000 soil particles, or in other words, gravel particles. And each one of these particles was made up of 3 spheres. And this is a gravel model that is a validated model in EDEM, so we can have confidence in its behavior. And again, it's not just the shape, but it's also the friction and cohesion parameters. And so these blue arrows are representing the different loads. We have the normal loads, and then the vertical arrows, and then the side-to-side arrows are representing the tension and basically the pull-out force ultimately. So this animation here is showing the simulation process. So hopefully it's appearing well on your screens. But initially we gradually apply a normal force and let the links come to a halt, and then we start changing these front back type forces. And you can see at a certain point, the velocity gets to be pretty high. So if one were to think about friction, what is the friction? I mean, and this is what this towing operation is all about, is to look at how much traction is available, and traction is related to friction. So in the case of basic friction between two rigid bodies, we're used to the notion that we have a coefficient of friction for the static case with no relative velocity. And then as we get the relative velocity, then that dynamic coefficient of friction is lower. So it turns out that's not exactly the case when we actually put in the details of the particle track interaction. Rather, the friction, the effective coefficient of friction actually increases for a time with the relative velocity. So basically, as the track is, digging in and interacting with the particles, it can basically handle a higher and higher, breakout force as it's interacting with the particles, but then as the relative velocity gets, high enough, then that's when it breaks free. So it actually increases for a while as the force is increased, the breakout force. With the relative velocity, the force that can be resisted is increasing for a while, and then when it breaks free, then the force heads towards a much lower value. And then looking at the, we tried also different soil characteristics, and what we found was, as we applied the normal force, if the cohesion of the soil was too low, the track shoes could push into the soil, and so that was good to push into the soil. But then with the low cohesion, then it couldn't resist these breakout forces. And so as the cohesion was increased, there was a certain value where you could get the maximum breakout force, where the cohesion was high enough to resist the breakout force, but it was low enough that the track shoes could engage with the soil to a sufficient extent. So that was our simulations. And then from the simulations, we came up with curves where we're looking at different properties, which could be different normal forces and so forth. And then we'd come up with a family of curves, and we could look at what were the different resistive forces, and also what was the sinkage. So on the lower right, this is a plot showing sinkage for different values of normal force. And on the lower left is looking at the forces developed resisting the breakout event. And you can see at some point, the curve drops off, and that's when the track link is breaking free. So, and so as far as, the computational aspects of things, this work was done some years ago, and the computer hardware is faster now. But with what we were doing, the soil bin simulation took 5 hours to run. But taking the curves to describe the interaction of the track links with the soil, and applying that in the multi-body dynamics software, then the multi-body dynamics software could use those curves, and was able to run the full vehicle simulation up the slope in about 40 minutes per run. So what was included in the full vehicle simulation? Well, we had all the different track links in the track, so that was modeled in full detail. We had the different road wheels, suspension units supporting the road wheels, carrier rollers, sprocket, and idler. So these were all separate entities. And then, the whole of the vehicle and all the other equipment, that was just considered as just one single lumped mass. But all the suspension and the road wheels and so forth, all was modeled in detail so we could kind of see any dynamic effects there. The track also was connected with flexible connectors, so it could exhibit some kind of stiffness behavior. And likewise, we had stiffness and damping in the suspension. And all the contacts between all the track links and all the different components, all that was included. And then the soil subroutine was where we were using the curves generated by the EDEM outputs and then applying that to calculate what kind of traction was available. We were applying basically those curves to all the different track links. So here's a simulation showing the animation. So we're again using the EDEM data and now applying that with the multi-body dynamics software. And you can see we're gradually increasing the resistive force. And see now we've come to the limit of the vehicle. You can see it's starting to turn actually, but it couldn't pull up the slope any further. These red arcs are showing the torque that's being applied to the sprockets to be able to maintain the speed up the slope. So we have like a little controller model to set up value of those torques. And at the beginning it's a low torque on the flat part, but then it increases. So we did these simulations for different slopes. And then let's see what the results would be. And this is, a typical result. So we have two different curves here. The blue curve is showing the velocity of the vehicle. So we ramped up the vehicle velocity to about 47 inches per second. And then as we started going up the slope, then that speed slowed down. Initially, the torque was increased. It kind of flattened out here for a while with the higher torque. You can see some kind of waviness here. And then at some point, it's like things dropped off because that's where the track links were breaking free of the gravel soil. And what we did here with the pintle force is, we waited until the vehicle was, operating steady state down the track. Then we gradually increased the pintle force, and then we started taking these steps. And the reason we have these steps is that if as one is increasing the pintle force, it may be at a limit where the track is ready to break out, but the velocity will continue, with just due to inertia. So by having these flat segments, then as that force was applied, then that gave the vehicle a chance to lose its inertia and then start to slow down. And so this was the way we found to be able to get a good idea of when the track was going to break free. So as we had this data from the simulations, then we also had test data. And we actually had data from 12 different tests. It had different vehicle configurations. As you can see here, there was a certain number of configurations that had track type number 1. The other configurations have track type number 2. And then we had the different slopes, high and low, and different recovery vehicle weights. And so from all the test data, basically what we had that we could really rely on was really a pass-fail output from each run. Could the recovery vehicle pull the other vehicle behind it all the way up the slope? And so on two of the physical tests, this VL4 and the VL6, the vehicle or the towing vehicle or recovery vehicle was able to pull the towed load up the slope but it was barely able to do so. So that was some more specific information than just pass fail. So we use those two cases to basically get everything tuned. So we adjust the soil model parameters, and until we also had a situation where the recovery vehicle was able to pull the other vehicle up the slope, but it was just barely able to do so. So we did that for each track type. So that's why we picked VL4, VL6, because it was two different track types, and both of them was a marginal success. And so then we use those runs for tuning. Then the other 10 runs, it's like, okay, if we match the results on the other 10 runs, then maybe we have a good validation to the model. And as you can see, with all the other runs, we were able to predict whether or not the vehicle could tow its load up the slope or not. So we had perfect accuracy. Of course, it is a pass-fail, but that gave us confidence in the results. And then the next step was to do some design studies. So here in the lower left, that chart is showing, we looked at 9 different possible changes to the design, and then we assessed what improvement that had on the towing capability. And this gets, to looking at the sensitivities, like I discussed earlier. And for example, it's very useful to see that changes related to design 7, 8, and 9, we can see that they had virtually no effect on the performance of the vehicle. So that's really helpful to establish, what matters and what doesn't. So then we took the most promising design changes and tried combining them together and tried to see what kind of improvement we could achieve. And you see here that with designs 1 and 6 put together, we had close to a 50% improvement in towing capacity. So that was very useful information to our client. So in conclusion for this case study, we are able to successfully determine, what are the results coming from different design changes with regards to towing performance, and to be able to actually do that for a soft soil, in this case a gravel, and with different slopes. And in order to help our client be able to focus on what kind of design changes to make on a possible future vehicle. We use discrete element modeling, discrete element method to capture this complex soil track interaction. We learned kind of what the effective friction behavior was like, what the different limits were before breakout occurred. And we were able to significantly reduce computation time by doing this soil subroutine usage of the curves developed from the EDEM data. And then, so have very detailed soil in the first model, and then use the soil subroutine, and then have the full vehicle simulation with all the track links and everything else in the second round of simulation. And that was very efficient. And we were able to evaluate many possible design changes, and much more than what the client could have done with actual physical tests. These are the references, from this case study. So you can see there's a lot of activity going on, even in just this one area. But I'd say overall, different simulations people are doing in many different industries. It's a huge amount of activity. So overall conclusions, the EDEM discrete element modeling software can accurately represent the behavior of bulk materials of all kinds. And then it can be used with multi-body dynamics software such as MotionSolve or Recordine, replicate mechanical system behaviors as they interact with bulk materials. And a true insight, and ourselves at EngineSoft, we work together to provide clients with high quality software with the associated support and excellent consulting services to help people solve their problems, in a very effective way. So with that, I am done. I'll turn it over for any questions.